Welcome to the Infinite Geometric Series video. This is our last lesson for this unit and for the rest of this semester. So an infinite geometric series has an infinite number of terms. That means that this series can go on forever and ever and ever. A convergent series is a series with a finite number of terms in which the partial sums approaches a fixed value. So for example, 1 plus a half plus a quarter plus 1 over 8. Eventually, this is going to converge towards 2 because all these numbers are going to get smaller and smaller and smaller, and if you add them up, they're going to be less than 1. A divergent series is a series with an infinite number of terms in which the sequence of partial sums does not approach a fixed value. In other words, it's going to approach infinity just because the sum is going to become larger, larger, and larger. So the sum of an infinite geometric series where r is between -1 and 1 can be determined using this following formula. S infinity is equal to the first term divided by 1 minus r, where r is your common ratio. So we're going to find the sum of an infinite geometric series. So when we do that, we have to decide if it converges or diverges. And if it converges, then we can find a sum. So what we're going to do over here, we need to find what r is. We know what t1 is. T1 is 32. And to find r, all I have to do is take the second term and divide it by the first term, which is equivalently 1 over 4. Or you could have done 2 over 8 or 0.5 over 2. You're still going to get r equals 1 over 4. So let's see what we get here. Because r fits in between -1 and 1, then we know that this series converges. Now, if our r does not fall within -1 and 1, then we know that our series will diverge. Okay, so let's find the actual sum of our convergent infinite geometric series. So t1 is 32. We're going to divide it by 1 minus r. In this case, that's a quarter. 1 minus a quarter is 0.75. And this is equal to 42.7. So that is what our geometric series is going to converge to. Moving on to the next one. We know what t1 is 100. That's the first term. And then we need to find what our common ratio is. I'm going to take the second term and divide it by the first term. Remember to include the negative in there. So this is going to be -1 over 10. Again, this r is going to fit in between -1 and 1. So our series is going to converge. And we can calculate S infinity, which is going to be 100 divided by 1 minus 1 over 10, which is 100 over 1 plus 1 over 10. Or 100 divided by 1.1, which is 90.9. So that is our total sum for this infinite geometric series. For the next one, same sort of scenario, we're going to find what our common ratio is. We can take our second term and divide it by our first term. So we know r is -1 over 3. And -1 over 3 fits in between -1 and 1. So our series is going to converge. And S infinity then is 1 over 1 minus our r, which is -1/3. In other words, that's 1 over 1 plus 1/3. And if we put this in the calculator, our sum is going to be 0.75. One last example for this. We're going to find what r is. Our second term is -4. Our first term is 2. So r is -2. Now this is bigger than 1, or smaller than -1, I guess. Which means that it is outside of the range of -1 and 1. So that means that this series diverges. And we can't find a sum for it. Now the last type of example, we can use our formula for the infinite geometric series to help us find a fraction that can be equal to a repeating decimal. So what we're going to do is rewrite 0.49 repeating, where the 9 is repeating, as 0.4 plus 0.09 plus 0.009 plus ... And this is equivalent to 0.49 repeating. So the rule is you're going to write down whatever is not repeating. So in this case is 0.4. And then you're going to rewrite it so that we have a repeating decimal after that. Equivalently, I can also write this as a fraction. So I'm going to leave this 0.4 as is, but I can rewrite 0.09 as 9 over 100 because that's 9 hundredths. And this would be 9 thousandths, and so on. So if we just look at this portion of how we've written 0.49 repeating, this can be written as maybe a series. So if that's the case, I'm going to say that this part here is T1 is 9 over 100 as our first term, and our R is 1 over 10 because I would multiply 9 over 100 by 1 over 10 to get the next term, which is 9 over 1,000. So if that's the case, I can find the sum of this series by taking, well, I'm going to leave 0.4 alone because that doesn't change, but I can rewrite this as the formula as T1 over 1 minus R. So T1 in this case is 9 over 100, 1 minus, and then R is 1 over 10. And then I can simplify this and see if I can rewrite this as a fraction. So then we have 9 over 100 over 9 over 10. Seems like our 9s are going to cancel out here. We're going to be left with 0.4 plus 1 over 10, which is 4 over 10 plus 1 over 10, which is 5 over 10. So in this case, we couldn't really write a perfect fraction to express 0.49 repeating. The only way we could write a fraction that would be close enough to 0.49 repeating is 5 over 10, which kind of makes sense because 4.49 repeating is very close to 0.5. Now, when you do examples on the next page, you should get better looking fractions. It's going to be these questions over here for question 3. And in this case, it can just give me an idea of how to get started. But you don't have like that 0.4 that stays stable. Instead, you're going to have 0.63 plus 0.0063 plus 0.00063 and so on. I'm going to write this as 63 over 100 and write these as fractions. And then you're going to use your infinite geometric series formula to determine what that's going to look like as a fraction. And so that is it for this lesson. I hope that you had a good semester in learning pre-cal and you're basically set for next year to take grade 12 pre-cal. And I hope you all have a great summer.